Hi, my name is Simon and I will be presenting BeAFix, a technique for automatic alloy model repair. Given a problem for which we want to construct a program, a usual approach is to write the program, evaluate it against an expected solution, specific scenarios for example, and modify the program whenever it's found not to meet the expectations. One way to reduce the issues that arise during implementation is with formal specifications. Specifically, those related to the problem domain and program's design. These specifications are much more abstract but nevertheless not trivial to write, and errors can still be made. In the same manner we have an expected solution with which to contrast our program, we can have formal properties that our specification is meant to satisfy. A similar cycle of validation and fixing then occurs, although this removes future issues we will have in our program, leaving the more technical ones to deal with. Let us focus in the spec and properties part. The specification will involve specifying the problem domain and the solutions related operations, while the properties will involve things that must happen and things that must not happen. Considering linked list with a repo-k, empty, acyclic and contains operations, the first three will take a list and return true or false with respect to if the list is valid, empty or acyclic, respectively. Contains will take a list, a value, and return true if the list has an element with that value. Some expected properties will be: expecting that there should exist lists which are both non-empty and acyclic. If none exist, then we should either fix our domain restrictions and/or buggy operations like empty and acyclic. All empty lists should be acyclic. If an empty list which is not acyclic can be obtained, then we should fix operations empty and/or acyclic. And for every valid list, those that satisfies the repo-k, if the operation contains return true for a particular value, then the list must not be empty. If one list and value exist such that it violates this property, we might need to fix repo-k, empty and/or contains. In this paper we will focus on alloy, a declarative language based on first-order relational logic which uses bounding verification via subsolving. We will refer to the domain and operation specifications part as the model, and the properties stating what must and must not happen as the oracle. The development cycle for an alloy model will follow the same cycle we saw before, validating a model against some expected properties and using a subsolver to check if some property is violated, which is highlighted by some feedback like no instances being obtained or a counterexample, in which case we will modify or repair the model and keep going until all properties hold. Our goal in this paper is to automate this cycle. Our technique will start with a model and an oracle with at least one failing property. After localizing the potential buggy expressions, we can now see our model as a set of expressions to repair. Let's keep our example of list and assuming we have one expression marked for acyclic, two in contains and one for empty. Using mutation operators, we will then generate mutants for each expression, starting with acyclic and continuing with the rest. Each candidate will result in two kinds of descendants: those for which the same expression will be mutated again, and those for which the next expression will be mutated. All previous expressions will remain fixed. Our search can then be modeled as a tree, starting with the original model, which we will traverse in a breadth-first search manner. A repair candidate can now be seen as a path in this tree. Consider now a repair candidate that has two fixed mutations, one in acyclic and one in contains first expression, and also that this candidate does not satisfy the oracle. We should now continue the search by looking all possible mutants for the next two expressions. One way to avoid some candidates will be taking the expressions yet to be mutated, second expression of contains and the one in empty, and ask if there is some expression for each one of those that could be used to satisfy all properties. If this can be done, the exploration will continue. If not, then the fixed part of the candidate can never lead to a repair. This will require high-order quantification, which alloy does not directly support. So we will instead ask if there is some possible value to be used, instead of the expressions to mutate, to satisfy previously failing properties on specific scenarios. This will reduce the useful properties to those that can generate a counterexample when violated, but allow us to make this check automatically. In a bit more of detail, we can see our current repair candidate as the following, with some mutated expressions that may use the related predicates arguments, and expressions yet to be mutated that may also use predicates arguments. What we can do is change those yet to be mutated expressions with particular relations that involve the same arguments and ask if previously violated properties on specific scenarios can now be satisfied by giving values to those relations. Continuing with our current candidate, let us assume there is a property which only involves the acyclic predicate. If this property is violated, we are sure that, given we will not make any more mutations to the acyclic expression, there is no way any candidate generated from the current one can ever lead to a repair. To summarize our technique, we mentioned that expressions to be mutated are defined or marked once at the start of the repair process. We rely on external fault localization tools for this, particularly we use FLAG, a new technique for fault localization in level models based on differences between assertions, counterexamples, and satisfying instances. Ours is a mutation-based repair technique with a parameterized set of operators that can be changed without much difficulty. We use a bounded exhaustive approach for searching a repair. This assures us that if a repair exists on a given bounded space, we will find it. But the search space increases exponentially with respect to mark expressions and mutation operators used. A breadth-first search approach to visit the candidate space results in always producing, when found, the closest repairs, with respect to syntax changes. Finally, our pruning technique is sound. Any prune candidate will never lead to a repair, but not all prunable candidates will be pruned. At the time we proposed our technique, the state-of-the-art and seminal work with respect to automatic alloy model repair was repair, a technique that uses test as oracle, spectrum-based fault localization, and a combination of mutation operators and expression synthesis. We compare the technique against repair using both repair's own benchmark and alloy for fun benchmark. On repair's benchmark, repair fixes 26 out of 38 models, with 10 of them being overfitting, evidencing that the test suite used as an acceptance criteria is too weak, requiring additional tests, while BeAFix repairs 24. On alloy for fun benchmark, repair fixes around 80% of models, with 71 being overfitting, again showing the need for more tests to be added, while BeAFix repairs 47%. In both cases, it's important to remark that even when considering all repair's fixes, both techniques are complementary. Some models can be repaired by both techniques, but some are only repaired by the only one. This has to do with some basic differences between both techniques. repair is not exhaustive and will rerun fault localization on each iteration. BeAFix is exhaustive but relies only on mutations, while also relying on fault localization only once at the start of the process. With respect to overfitting, BeAFix can use both property-based and scenario-based oracles, but will benefit from property-based oracles being stronger than test. repair, on the other hand, can only use test and requires manually crafted tests to avoid these spurious repairs. When manual tests are used along automatically generated ones, it can correctly fix 26 models of the repairs benchmark. If anyone wants to use BeAFix, we have a replication package available, as well as the tools repository. The fault localization technique will also be presented in this edition of ICSE, and we also have a replication package available. Thank you for your time.